In this lecture, what we're going to be doing is we're going to be solving an air conditioning problem involving a system that is not at atmospheric pressure, and consequently we are not able to use the psychrometric charts, and consequently what we're going to have to do is use the different equations that exist in the book or were covered in an earlier lecture. And the solution procedure for this type of a problem is in a way kind of like solving a puzzle. You look at what you know and what you don't know and then try to work it out. But I'll begin by writing out the problem statement and then we'll work through the problem. So there's our problem statement. What we're dealing with is an air conditioning system operating at 95 kPa. It's right there. That's the first indicator that we cannot use a psychrometric chart unless you have one that is corrected for that altitude or that pressure. And what it is doing is supplying wet steam. So what we have is a heating section. We're given some of the conditions of the air coming in. We're told that the wet steam is at 100 degrees C saturated water vapor, so we can get property data off the steam tables for that. Air is entering at 10 degrees C, 70% relative humidity. We're given the flow rate, and it leaves the humidification or humidifying section at 20 degrees C, 60% relative humidity. And then they have the list of a number of different things that they want us to calculate. So what we're going to do is we're going to write this out in terms of a schematic. So we have state 1, state 2 after the heating, and then state 3 after humidification. And we're given some of the information in terms of what different things are. Here we have saturated vapor at 100 degrees C coming in. Other pieces of information, we know that the inlet temperature here is 10 degrees C. 70% relative humidity, and volumetric flow rate is 16 meters cubed per minute. And we know the pressure in the system is 95 kPa. And finally on exit we have 20 degrees C and 60% for our relative humidity. Now what we want to find in this problem, we want to find, first of all, the temperature after the heating section, so T2, and they also want us to get the relative humidity at that location. The next thing they want to know is how much energy or thermal energy we're putting in on the heating section. So that would be Q in. I'll draw that here as Q dot N because we're heating. And the last thing they want to know is how much liquid are we adding, or water, so the mass flow rate of water N, which should be up here, M dot N. So those are the things that we want to find. What we're now going to do is we'll proceed through the analysis. And again, like I said, this is kind of a complex problem, a lot of things going on. So the best thing to do is start working with what you know, and then you'll slowly work your way through. So for the analysis, the first place that we can start, first of all, P does not equal 1 atmosphere. Therefore, we cannot use psychrometric charts. Second thing, at state 1, we have 10 degrees C, and that's our dry bulb temperature. But with that, what we will do is we can go into the steam tables and If you recall, when we were looking at the properties of air-water vapor mixtures, we had different equations enabling us to get different things. And we talked about the partial pressure of either the dry air or the water vapor. And so this was the technique that we used, enabling us to get the different pressures, partial pressure for either the water vapor or the dry air. And so from this, we can then determine the value of the partial pressure due to the water vapor. And then, of course, the atmospheric pressure is going to be addition of both the dry air and the water vapor. And from that, we can use it to determine the partial pressure of the dry air. So we get the partial pressure of the dry air, 94.1407 kPa. So we have that pressure. Now what can we do with it? Well, one thing I want to do to begin with, I want to convert the volumetric flow rate into a mass flow rate. So what we're going to do, we're going to use the ideal gas equation to determine the specific volume of the dry air, and then we're going to go and figure out what the mass flow rate of dry air is in our system. So that's what we're trying to do here. Writing out the ideal gas equation. We can rearrange it in terms of specific volume. And I've written the volumetric flow rate in terms of meters cubed per second instead of minutes. Sorry, I've skipped a step here. Part that I missed was computing the specific volume of the dry air. (10 degrees C is 283 Kelvin. So that there is the specific volume of the dry air. We can now take this and use it to compute the mass flow rate of air. So that is the mass flow rate of dry air in our system. What we'll do in the next segment, we'll continue on working this problem, but we'll take a look at the mass balances for air and water and see how we can progress there. And then eventually we will get to an application of the first law. So I'll stop it there for this segment, and in the next segment we'll take a look at the mass balances.